Okay, Assalamualaikum warahmatullahi wabarakatuh. I'm from Group 39 and today I'll be presenting to you our plant design project 1 entitled Biogas and Biofertilizer Production from the Palm Oil Mill Effluent, which is POM. Our supervisor for this project is Dr. Azizul and we have 5 group members, which is me, Nur Ilhami, Amjad Usni Zaim, Yani Adriana, Muhammad Nazmi and also Tristan Raj. Okay, first I will proceed with the introduction part of this project, which is the productions of biogas and biofertilizer from the POM started with the raw material that we use, which is the POM, palm oil mill effluent that consists mainly of water and a mixture of the palm oil derived chemical. And the main purpose of this project is to study and develop a conceptual process design for biogas and organic fertilizer productions. And as we all know, the raw foam itself has a brownish, viscous and voluminous appearance, and also thick that contains of 95% of water, 4 to 5% of total solid, and roughly 0.6% of oil. And the discharge of the foam from the palm oil is heavily regulated due to its harmful effect to the environment. That is why the government and also the environmental organization has given the standard discharge for the certain parameter of the palm oil itself. They contain a few parameters, which is COD, BOD, total solid, nitrogen, pH, certain pH that need to be considered, and also temperature. Okay, the two main expected products resulting from this plant are biogas and also fertilizer. As you all know, biogas is a product from the reaction treatment used, which is in this project, we use anaerobic digestion. There is a breakdown of the biodegradable material in absence of oxygen, containing gas mixture that contain mostly of the methane gas, CH4, and also the CO2. While the main product of the anaerobic digestion is a biogas, the residue from this process, which is a byproduct from foam, is a fertilizer. And the fertilizer itself can be used for other purposes. And generally, the higher the percentage of the methane gas, CH4, in the biogas, the higher the quality of the biogas produced. Okay, for the literature review part, the biogas itself is an emerging source of fuel that have the similar application to the natural gas. While the composition is slightly different, but the potentials of biogas as a green and renewable source of energy is very attractive. As you all know, biogas is very environmentally safe and economically sustainable product that can be used as our source of energy. And the quality of the biogas produced are usually evaluated by the percentage of methane, carbon dioxide, and also the hydrogen sulfide produced. For the hydrogen sulfide, as you all know, it is usually removed from the gas in order to improve the quality of the fuel. And as you all know, since it will form in the presence of air moisture, the hydrogen sulfide form will be highly acidic and corrosive. That is why, ideally, in a biogas production, we want to reduce the percentage of the hydrogen sulfide and also CO2, but high percentage of the methane gas. This is the compositions of the biomass from the biomass material. Okay, for the market analysis part, according to Malaysian Palm Oil Berhad, the palm oil industry produced for about 18.7 million tons of the crude palm oil. And this abundance of the palm oil mill as an effluent of the palm oil industry can be increased due to its economic value. And since the production of the palm oil is very consistent throughout the year, the raw material for biogas, in this case is palm, is not short in supply and readily available in the palm oil mill. Current demand on biogas are affected by a few factors involved, such as renewable energy has become the choice of energy source to reduce the dependency on fossil fuel. And one of the renewable energy identified is the exploitations of the biomass from the palm oil as our source of energy. And for every tons of the crude palm oil produced as estimation, there is for about 3 tons of the palm oil mill effluent that will be generated. And all the foam that is converted to biogas can be produced from these different type of ways. And lastly, it is considered as green and renewable energy as we treat our waste and we reduce our dependency on fossil fuel as our main source of energy. Moreover, through purifications of gas, biomethane produced has the same quality of the natural gas in terms of the methane and can be used as vehicle fuels. And from the graphs, we can see that the number of operating palm oil mill is increasing from time to time. Okay, next moving on to the crucial parts of the designing a plant, which is the plant location. As we all know, for the plant location, it is very crucial to consider a few factors, and it is very fundamental to consider what we need to prioritize in our plant designing. Plus, the site itself should be in the position to provide a reasonable location for multiple phases of potential plant growth. In continuation, it also must have a favorable environment and a safe living condition for easy operations of the plant. Thus, a few factors have been taken into account, which is the location factor that have availability of raw material, market demand, energy, transportation, wastewater, water supply, labor supply, site characteristic, fire and flood, and also the community factor. And based on all these factor consideration, the suggested location is in the Tapah Perak, which is Syarikat Cahaya Muda Perak. Since it have the most highest weightage of the availability of raw material, which is foam that can drastically reduce the cost of the transportation. Okay, next moving on to the plant layout. For the plant layout, it is very effective since we have to ensure the effective physical arrangement that involve the processing equipment, services, and it is fundamental to be fully established. Since we need to permit the quickest flow of the raw material at lower cost and minimum handling. And that is why there are a few necessity of the plant layout, including proposed future expansion area, production area, which is the processing area, admin area, and also the storage area. And for all this part, the storage area were basically stated at the back of the plant, and the production area we have considered it's near to our storage tank and also our fertilizer tank. That's all from me. Thank you.
Hi, my name is Amjad and I'll be explaining about process screening. So for this project, we have two main concerns of process screening, which is first is reaction and the second is for the CH4 purification. So for the reaction part of process screening, we are looking into two types of digestion, which is anaerobic digestion and aerobic digestion. As its name suggests, these two differs most on whether they react in the presence of oxygen or in the absence of oxygen. So for anaerobic digestion, there is no aeration required. It has a low energy cost to react and high yield of biogas. The residue sludge of anaerobic digestion can also be used as fertilizer because it contains all the necessary minerals required as a fertilizer. So for aerobic digestion, on the other hand, occurs in the presence of oxygen, requires active aeration in the reactor, which also contributes to its already high energy cost to react, and it has a low yield of biogas, which we would like to avoid. So another one that is that the residue sludge is unsuitable for use as fertilizer, which defeats the purpose of this project to produce at least two types of products. So we have decided to proceed with anaerobic digestion, as we can produce two types of product, which is methane and the residue sludge, which can be used as fertilizer. So elaborating more on anaerobic digestion, it consists of 4 different stages. So the first stage is hydrolysis, where it breaks down insoluble long-chain polymers. So POM contains long-chain polymers of fats, proteins, and carbohydrates. So hydrolysis breaks down those long-chain polymers into shorter chains of polymers. So this shorter chain of polymers consists mostly of fatty acids, amino acids, and sugars, which will then be converted in the acidogenesis stage. So bacterial acidogenesis bacteria will convert these fatty acids, amino acids, and sugars into carbon dioxide, hydrogen, and ammonia, and also organic acids. In the next stage, acetogenic bacteria will convert the organic acids from the acidogenesis into acetic acids, where then methanogenic bacteria will convert those acetic acid into gases, which consist mostly of methane. So moving on with the CH4 purification for the process screening, there are a number of processes available for CH4 purification, and for this particular project, two routes were shortlisted. The first is water scrubbing, and the second is amine scrubbing. So water scrubbing involves a physical absorption principle, while amine scrubbing involves a chemical absorption principle. So after simulation, it was found that amine scrubbing has a higher purification efficiency, meaning from the process we can create a higher percentage of methane gas. So we decided to proceed with amine scrubbing as our main process for CH4 purification. So the process basically goes like this. So the raw gas or biogas that evolves from the reactor will go through absorption column, which is fed with amine. We will discuss what type of amine in later parts. So the amine will absorb all the non-CH4, all the contaminants in the CH4 gas or the biogas, and so the CH4 will leave the absorption column as a high percentage of CH4 compared to the other components such as CO2 and so on, and H2S. So from there, the dirty amine, which contains all the CO2 and H2S, will go through a separator or distillation column to remove those gases from the amine, and then the amine will be recycled. So in this process, theoretically, the amine will be recycled endlessly to achieve its purpose. Right, so I'll pass the to Nazmi for mass balance.
Before simulation of the process is carried out, the preliminary mass balance is calculated first. From literature, it is found that 1 meter cube of foam is able to produce 3 meter cube of biogas. Using 1158 kg per hour as the basis of biogas mass flow rate, which is chosen based on site selection, we can calculate the amount of foam to be used and the amount of fertilizer that can be produced. Using the density of raw biogas, the volumetric flow rate of raw biogas is calculated to be 1007 meter cube per hour. From the ratio of foam to biogas, which is 1 to 30, foam volumetric flow rate is found to be 32.6 meter cube per hour. Then, after converting the unit to kg per hour, and by using simple mass balance, the amount of fertilizer mass flow rate produced is 32,442 kg per hour. And this is the composition of biogas that is used in further calculation. The value given in the literature is in range. However, for simplicity, we took the average value of the range for each element to be used in the calculation. Then a simple mass balance is calculated at the separator V100, at the absorber T100, and also at the stripper T101.
So I'll be explaining further on the economic analysis for this project. So for the economic evaluation, we did two types of economic potential, which is EP1 and EP2. So for EP1, it is the product cost minus raw material cost. So for the raw materials, we have POM and water, which is added back to, which is top up in the amine stream. For the products, we have the biogas. So this is the biogas that has been purified, and the fertilizer. So we calculated the flow rates, the annual capacity for 330 operating days per year. We find the price ratings and the total price based on the annual capacity. So for POM, however, we don't have any price because we are taking that POM from the palm oil mill from the location that we plan to build our plant at. So the calculation for EP1 is as shown in the slides, which brings to 64.3 million for EP1. And for EP2, EP2 is product cost minus raw material cost minus utilities cost. So it can be simplified that EP2 is EP1 minus utilities cost. So for this part, we calculated the utility cost, which consists of the heaters, coolers, and pump. So the total utilities cost total up to 16.8 million per year, and calculating EP2, which is EP1 minus utilities cost, we get 47.47 million per year for EP2.
Now I'm going to present the process flow diagram of our project. And as you can see here, this is the PFD of our project. Foam enters the anaerobic digester, and after a certain time, the raw biogas is produced at the top, and the remaining sludge becomes the biofertilizer. Raw biogas is stream 2 enters separator V100 at a temperature 30 degrees Celsius and pressure 500 kPa to remove any free water that contains in the raw biogas. Then it enters at the bottom of the absorber T100 at the same temperature and pressure, and the treated biogas, which is the stream 14, exits at the temperature 35 degrees Celsius and pressure 200 kPa. Also, as you can see here at the top of the T100, lean DEA, which is stream 11, enters at the top of the absorber at the temperature 35 degrees Celsius and pressure 200 kPa. After the lean DEA absorbs the H2S and CO2, it becomes the rich DEA. The rich DEA exits from the bottom of the absorber and passes through expansion valve PCV100 to reduce the pressure from 210 kPa to 160 kPa at constant temperature. Then it enters a heater E101 to increase the temperature from 40.7 degrees Celsius to 60 degrees Celsius before proceeds to stripper T101 to remove the acid gas from the rich DEA. The acid gas, stream 16, which contains high content of H2S and CO2, exits the stripper at the top at a temperature of 98.8 degrees Celsius and pressure 110 kilopascal. The lean DEA, which contains low or almost zero content of H2S and CO2, exit at the bottom of the stripper and pass through a cooler E102 to reduce the temperature from 117 degrees Celsius to 87.7 degrees Celsius. Any loss of water in this process is compensated by the makeup water here. And then the stream passed through another cooler E103 to reduce the temperature to 35 degrees Celsius and pumped to increase the pressure from 130 kilopascal to 200 kilopascal before recycled back into the absorber. The description of this PFD can be found in the next slide.
Assalamualaikum and a very good day everyone. I am Yani Adrena and I will be presenting on the heat integration part. So first of all, I will be showing the process flow diagram for our process and the scope area where we will be applying the integration. So this is our scope of area, and initially for this process we have two coolers, which are the E102, the first cooler, and the second one is E103, and we also have one heater, which is E101. So by applying heat integration, we will try as much as we can to reduce the number of utilities in this process. So moving on to the stream identification. So for the minimum temperature difference, we will be using 10 degrees Celsius. And we have three streams here, which is the first one is cold stream, and we are required to increase the temperature from 40.73 degrees Celsius to 60 degrees Celsius, and the heat flow is 876.11 kilowatt, while the heat capacity flow rate is 45.46. And the next one is the hot stream. So we are required to reduce the temperature from 117.8 degrees Celsius to 87.78 degrees Celsius, and the heat flow is 1436 kilowatt, and the heat capacity flow rate is 47.83. And lastly is the hot stream, where we are required to reduce the temperature from 85.767 degrees Celsius to 34.99 degrees Celsius. And the heat flow is 2360.28 kilowatt, and the heat capacity flow rate is 46.57. So moving on to the problem table algorithm PTA and the cascade. So this is our PTA and cascade. So from the PTA, we are able to obtain information on the minimum utilities requirement. And from the cascade, we know that we need 0 kilowatt for hot utilities, and for the pinch temperature, where it is the point in the heat exchanger where the temperature difference between hot and cold fluid is at its minimum. And in this process, our pinch temperature is at 82.78 Kelvin. And lastly, we are able to obtain information on the cold utilities that are required, and in this process, we require 2920.17 kilowatt. So, the heating and cooling requirement of the process is modeled through the cold and hot composite curve, and from the composite curve, we are able to know the process-to-process heat transfer area, and we can also know this from the grand composite curve. So for the composite curve, here where the hot composite curve and the cold composite curve are overlapped, this is where we know that the process-to-process heat transfer area can be occur, and we can put heat exchanger here. Then for the grand composite curve, it's the same, and this is called the pocket heat recovery, where the process-to-process heat transfer can occur. And next, moving on to the heat exchanger network design. So from this grid diagram, we are able to know that we can apply heat exchanger from stream 1 to stream 3, and we also need two coolers here for stream 2 and stream 3. So next is the utilities reduction of the heat integration. So initially we require 876.11 kilowatt, and after heat integration we manage to reduce it to 0 kilowatt, and this implies that the utilities reduction is 100%, which is very good. And next, for the coal utilities, before this, for the heat integration, we need 3,796.28 kilowatt. And next, after heat integration, we managed to reduce it to 2,920.17 kilowatt. And the utilities reduction for coal utilities is 23%. So this is also an improvement, and it's also good for the process. And basically, for all overall, we managed to get utilities reduction of 37.5%. So for the savings for hot utilities is 876.11 kilowatt. On the other hand, for the coal utilities is 876.11 kilowatt as well. So next, I will be showing the process flow diagram before heat integration. So before this, we have two coolers and also one heater. And after heat integration, we managed to reduce it. Now we have one cooler, and the rest of the streams we will be using one heat exchanger here. And that's all for me for the heat integration part. Thank you so much.
So, very good day to the examiners. My name is Tristan Raj. Today I'm going to explain about the process control and instrumentation and PNID and also HAZOP. So without further ado, let's begin. So basically, process control and instrumentation of the system is the most important part of the process plant. This is basically just to ensure a stable production rate and also produce quality product. So various elements available such as machineries, actuators, sensors, transmitters, modules, and also control valves. There are several control strategies used, one being feed forward, feedback, cascade, and also ratio. And three components that is focused in the control system is manipulated variable, control variable, and also disturbance variable. So manipulated variable is basically manipulated to achieve desired set point, and the control variable is a measured variable that is required to be controlled, and also disturbance variable is a variable that will cause changes to the control variable. So say these are the four types of control strategies, being feedback, feed forward, ratio, and also cascade. So feedback measures the control variable and also adjusts the manipulated variable to reach a desired set point. Feed forward, on the other hand, it measures the disturbance before the process offset. Ratio is used to maintain the ratio of two process variables, which are manipulated variables and also disturbance variables. Cascade consists of two monitored variables, and these two are usually control variables. So the first is reactor, RO1. The control objective is to control the level of liquid in the reactor, and also to control the pressure in the reactor. The type of controller used are feedback. So what happens here is that the control variable is measured first, so the reactor level and also the reactor pressure are measured first. Then the inlet flow rate of reactor and also the outlet gas flow rate of reactor is manipulated or adjusted until it reaches the desired set point. Next is the absorber T100. The control objective is to control the flow rate of liquid into the absorber and also to control the pressure in the absorber. The type of control we use here is feedback as well for both. So what is done here is that the flow rate of liquid into absorber and also the absorber vessel pressure is measured, and the inlet flow rate of absorber and outlet flow rate of absorber is adjusted to meet the desired set point. Same here for distillation column, the type of control used is feedback. The reboiler outlet temperature is measured, and the inlet steam flow rate of reboiler is adjusted. Same here for cooler, as outlet steam temperature is measured, and also the flow rate of cooling water is adjusted to just inside that one. Here, however, for mixer, the type of control used is ratio control. This is basically to control the feed ratio into the mixer. So the ratio of manipulated variable to this disturbance variable has to be the same before and after. So the flow rate of components before and then a mixer is to be controlled along with the inlet pressure and temperature. As you can see here, this is the PNID diagram. Yeah. Now moving on to HAZOP. So basically, what is HAZOP? HAZOP is Hazard and Operability Studies. HAZOP is a methodology used to study not only the hazards of the system but also its operability problems by basically exploring any deviation from the design conditions. So as you can see here, the HAZOP guide words used in this project is basically no or not, more, less, and reverse. The meanings are inside. The HAZOP analysis, for the first HAZOP analysis we did was for the stripper. So the stripper, there's like 4 nodes connected to the stripper. 1 is being the stripper, 2 is being the feed stream to the stripper, 3 is the stripper to the condenser, and stripper to the reboiler. So here you can see the condenser, reboiler, feed, and the stripper. So this is the first node. This first node is for stripper and it explains the guide word used for temperature. Parameter used to temperature, pressure, and level. Action is basically use alarm where appropriate, and mainly is to check the reliability and also to basically have proper maintenance, which most times is sufficient for any issues. Node 2 is the feed stream to the stripper. You can see is parameters used are flow and pressure, and same in action. Reboiler parameters used are flow, pressure, and temperature. The guide words given, possible causes, action, installation, high pressure alarm, and so on. Condenser parameter given is flow, pressure, and temperature. And now moving on to the second and final HAZOP analysis is basically absorber T100. So this only has 2 nodes, one being the absorber itself and the second one being the feed stream to the absorber. So this is the HAZOP analysis for the absorber, less or more. That means the usage of alarm for high flow. Yeah. And last and finally is the feed stream to the absorber. The parameters is the flow and pressure, and you see the actions are basically regular checking of flow controller, installation of alarm, and then again, like I said before, proper maintenance of parts. That's all. Thank you.
Alright, for the conclusion part, in order to develop a conceptual design to build a biogas and a biofertilizer plant, palm oil mill effluent were used as a feedstock, and based on design alternatives, selected alternative design were chosen that consists of separator, absorber, and also stripper for the productions of the methane gas. For the plant location, it is determined through a few factors involved, which include availability of raw materials, energy, transportation facility, and more. For the economic potential part, it were done mostly there are 2 phases of the economic potential, which is the economic potential 1 are done for the pump, water, biogas, and also the fertilizer. For the economic potential phase 2 were mainly for the utility involved, such as the heater component. And for process control and instrumentation, it were done to secure and control the plant operation based on its desired set point. Lastly, to ensure the safety and efficiency of the plant, HAZOP study were conducted in productions of biogas plant. That's all from me. Thank you.